So I'll be covering for Pat today and on Thursday. In today's class, we're going to study a recursive algorithm. It's going to be a sorting algorithm, MergeSort. The class will go like this. First, we're going to discuss the algorithm, talk about it, prove its correctness. Then after that, give an example and study its complexity. So we're going to study the MergeSort algorithm, which is like a recursive algorithm, a divide and conquer algorithm. And whenever we're dealing with a divide and conquer approach, a recursive approach, you just... Up?
Yeah.
Okay. Is it better now? Better?
A bit.
The volume is at max. It's pretty close. Is it better now?
Yeah.
Okay. So, whenever we're dealing with recursive algorithms, the really beautiful thing about them is like it feels like you're not doing anything and the problem gets solved. You just keep recalling the same function again, the same algorithm again, and the problem gets solved. But in our example today, not only the problem will be solved, it will be solved efficiently. And I'm sure most of you have done lots of sorting algorithms before in your previous classes. So today we're going to start first by defining what's the sorting problem. So, by the way, this is my first time writing in chalk on this board. If my handwriting is too small, let me know, or if it's too big, right? And my handwriting is bad, I know. Just ignore. So, given a list of n numbers from A1, A2, all the way till AN, the sorting problem is to return a list containing the same numbers in sorted order. So now numbers are going to be x1, which is going to be smaller or equal than x2, smaller or equal, all the way till xn. All right? So if these numbers are all unique, then we can say something like this. The set of numbers x1, x2, all the way till xn is equal to the set of numbers a1, a2, all the way till an, right? But if we have here the same number more than once, we would like it to also appear here the same number of times. So this is the definition of sorting. Now let's try to draft the MergeSort algorithm. The MergeSort algorithm will take as input these numbers, right? A1, A2, all the way to AN. So what should I do? We have here a recursive algorithm. What is the first thing that we do? I won't move on until ideas?
You break them into two parts?
So whenever we have a recursive algorithm, we have two pieces, right?
Yeah.
The base case and the recursive case, right?
Okay.
So what is the base case if you have a list A1 to n numbers? True. The list could contain one element, right? And if it has one element, then that element is trivially sorted. But the list could also have no elements. So if the list has 0 elements or 1 element, then we don't need to do anything. The problem is already trivially sorted, so we just return the list. So we can say something like If n is smaller or equal to 1, then what should we do? Do nothing, just return A1, A2, all the way till AN, right? This is what we do if we have one element or no elements in the list. So now what should we do? We know that this is going to be recursive. It's going to be a divide and conquer approach. So we have a list of elements. How about we split it into two pieces and we try to solve each piece alone? That's sort of like the most basic idea, the most basic thing we can do. So if you can do this, we split the list. So we can say that L1 is A1, A2, all the way to A n over 2 floor. That's the first half of the list. And we define L2 to be from the element after this one, which is an over 2 floor plus 1 all the way till an to be the second half of the list, right? So we split the list into two pieces, roughly equal size, and now we just call the same function on each part. So we can call MergeSort on L1 and MergeSort on L2, right? So this function is supposed to sort the numbers, and it's going to return a sorted list. Let's call it S1. This is going to do the same. So now the problem went from having a list of elements that we would like to sort to doing what? Now we have two lists. Each of them is sorted, and we'd like to merge them, hence the name MergeSort. And this is obviously an easier problem. If you have two smaller lists, and each one of them is sorted, and you want to merge them into a bigger sorted list, that is a lot easier than sorting a very large list. And we're going to see how to do that. So what do we need to do with these? We need to merge them, right? So we need to do S equals merge S1 and S2. And we'll figure out how this function will work later. But let's assume this will merge two sorted lists correctly. The problem is solved. So let's go over it again. We have this recursive algorithm where the goal is to sort a list of numbers. What are we going to do? Whenever we have anything recursive, we need a base case. And in our problem, the base case is having no elements on one element. Whenever that is the case, there is nothing to be done. So we just return the input. The problem is done. But if the list is larger than 1, then we just basically split the list into two equal size lists. And we call the same function to sort them. Sort each piece alone. And then each one will return a sorted list. And all we have to do now is to merge them into one large sorted list and return this. Okay? Let's see how we're going to try to do the merging. This will clear things out. By the way, if you have any questions, just raise your hand, right? So, the merge function will take as input two sorted lists, right? And it will return the full list of elements, which is going to be the same as this, but sorted. So what do we do? Let's do an example. What numbers are say we have 5, 7, 9, 15, maybe 3, 4, 10, 10, 18, 22. Right? So this is the input. Two lists that are sorted. And we would like to return a list S that contains all of the elements in this one and this one in sorted order. So here, what is going to be the first element of S? Can you see in the back, or am I writing too low on the board? You can't see. Okay. Can you see S2? Can you see S2? Okay. So we would like to get a list S that contains both of these elements, right? So what is going to be the first element in here? Because we know this is sorted and this is sorted, so it has to be either this element or this element, right? I don't need to look at any of the remaining elements because this is sorted and this is sorted. To determine the first element in S, I only need to do one comparison, which is here. I compare this one and this one. One is smaller, so I just copy it here. So now this is done, right? I copied the element 1. Now I have 3, and I have the smallest element of this list is now 5. So what do? I do the same thing. I compare the first element from here and the first element from here. 3 is smaller, so I just copy it to S. And I delete it from S2, right? Now again, the first element here is 5, but the first element of S2 is now 4. And I just do one comparison, 4 and 5. So 4 is smaller, I copy it, I delete it from its list, and I go to the next element. So I have 5 and 10. 5 is smaller, we delete it from its list, and then we do this, right? So let's write a small procedure to describe what we're trying to do here. Right? I'm just going to delete this for space. Right? So what are we going to do with this merge thing? What are we trying to do here? Well, do this. x1, which is first element of S1. And we get x2, which is the first element of S2, right? That's what we're doing here. Then what do? We just do a comparison, right? Do F x1 is smaller or equal than x2, and what do? We just add it to S. We're going to use the function append from Python, but you could use anything. This just means copy it to S. Append it with x1, right? And what do we need to do? Because we took x1, we should pop it. So pop x1 from S1. But if this is not the case, then x2 is smaller, right? So what do? Say else. Then we append S with x2, and we pop x2 from S2. So this is what we're doing, right? So let's continue from here. So what did we do? Now we reach 7 and 10. So 7 is smaller. We pop it. We compare these elements, 9 and 10. 9 is smaller. 10 and 15. 10 is smaller. 15 and 18. 15 is smaller. So we copy it. We pop it. So now what do we have? We have these elements left in S2, but we have nothing in S1. So what should we do? Because we know these elements are sorted, it's enough just to copy them to here, right? That's all we need to do. So we stop comparing elements whenever one of the lists is empty. Whenever one of them is empty, there is nothing remaining to compare. Just copy whatever is left and append it to here. Right? And once you've done that, you're done. So you can return S. So what we're going to do is, we can say, let me just this. Merge S1 and S2. So what are we going to do? We're going to say if S1 empty, if the first list is empty, then copy the second list, whatever is left of it, to S. So we're going to use another Python function, but what it just means is copy a list to another list. Right? So we extend S with S2, or whatever is left of it, and we just return S. Right? But if S2 was empty, we do the same thing. If S2 is empty, then we extend S with S1. And what do we do after that? We return S. Is this clear? Questions? Extend is basically what I just did here. I have some elements left. I'll copy all of them to here, to S. That's what it means. It's like copy. But it's like append is copying one element, extend is copying more than one, whatever is left there. Right? But something is missing, right? What did we do here? We did some kind of a loop. We compared two elements, we took the smallest one, then we compared two elements. So we need a loop to make it work, right? But because we have these returns here, the loop will just loop forever until we reach one of these conditions. So we can have something called while true. Right? I don't need to put the stopping condition here because whenever one of the lists is empty, this will take care of it. So, questions? Because that's the whole thing. Is it clear? Any questions? Okay, sure.
So you're only copying
I can't hear you.
you're only copying if there are two elements left over?
No, I copy whatever is left over, depending on the example. Like another example would be, if here I had 34, copy everything and just put it here, right? No, copy whatever is left of this list, right? Because we're popping elements out of it. Whatever is remaining, just take all of it. Okay?
And all this happens in a while loop?
Yes. Okay. But we're going to execute it only once. Because either the first list will run out of elements, or the second list will run out of elements. But whenever that happens, we'll just copy whatever is left and just return. Problem done.
Doesn't your pop get rid of the elements at the back of the list?
No, I'm assuming it's getting rid of here. We're assuming that pop is getting rid of the element here. You don't need to think, that's why I didn't write s1.pop. I wrote pop x1 from s, right? So it's doing what we want it to do. Okay? So now what do? Whenever we have a recursive algorithm, we have to prove that it's correct, right? And we always do that using induction, right? So the issue here is this. The proof is going to look a bit vacuous because in many parts of the proof, what we're going to say is, well, I looked at the code and the code seems to be doing what I want it to do. So the proof is not going to be very heavy proof. In many parts of it, we're just going to say, well, look at the merge function. Obviously, the merge function is going to merge two lists successfully because I inspected the code and the code seems to work. Okay? So let's do the proof. Right? So, we would like to prove that merge sort is correct. All right? So we're going to use induction because it's a recursive algorithm, right? So what do we do by induction on n, where n is the size of the list? So what should we do first? What do we do whenever we have an induction proof? Base case. We go for the base case. So let's do the base cases. Base cases. So first one we have is n equals 0. So we have a list of no elements. So this is trivially, I don't like it. Sorted, which means it's correct. What if we have one element? Because you can look here, right? We have two base cases, and can be 0 or a 1. Well, if we have one element, then it's the same thing. One element is trivially sorted. So the base cases are correct. So what do we do next?
Proof by induction?
Yes, this is the first part of proof by induction. So what do we call the thing that we assume? Inductive hypothesis, right? So we assume, I am going to need more space. We assume that MergeSort works. Am I using works? Let's use something correctly sorts lists or arrays, doesn't matter, arrays of length 0, 1, and all the way till n minus 1, right? This is our inductive hypothesis. And now what we want to do is prove MergeSort correctly sorts arrays of length n, right? So, and we're going to use the inductive hypothesis to do that, okay? So let's see what happens when we run an array or a list of length n on the MergeSort. What will MergeSort do? It will first, because we cover the base case, it will split it into two pieces, right? So it will do something like split it into L1 and L2, and then it's going to call S1. It's going to call MergeSort. MergeSort on L1, right? That's what we do here. We cover the base case. So we split the list into two parts. And now we call MergeSort on half of the list, right? So how long is L1? L1 is from A1 all the way to A n over 2 floor, right? Because n could be even or odd. But because we know that n is going to be bigger or equal than 2, right? Then definitely n over 2 floor is going to be smaller than n. Do you see why that's correct, right? If you have a number bigger than 2, if you divide it by 2, then take the floor. That number is going to be obviously smaller than n, right? Which means this function is going to run correctly. It's going to correctly sort L1. Why? From the inductive hypothesis. Because the input is of length covered by here. It's definitely in this range, right? And S2 will do the same thing. S2 will do MergeSort on a list of L2, which is going to be from A floor n over 2 plus 1 all the way to an, right? So we know the length of this is n over 2. This is L1. What is the length of L2? Well, L2, the length of L2 is going to be n minus n over 2 floor, right? So, how can we write this in a different way? Any ideas? N minus n over 2 floor.
Half of n.
But what if n is odd, right? I want an integer.
Oh, okay.
The length of a list has to. So, but what do? We use the ceiling function. Right? So this is called floor, and this is called ceiling. What do? They just round. The floor function will always round down, and the ceiling function will round up. Right? So, is this clear why the length of L2 is going to be the ceiling of n over 2? Well, let's say that n is even. Then n over 2 floor is just n over 2. And n minus n over 2 is going to be n over 2. If n is odd, one of them will round down, one of them will round up, and that's it. Right? So L2 will have length of n over 2. And because n is bigger or equal to 2, this is definitely smaller than n. Right? So, because of our inductive hypothesis, this function should correctly sort the elements of L2, because the length of L2 is smaller than n, and we just assume that it will do that correctly. Right? So what is left? What is left is to do merge. Now, in the case of merge, we're going to first check the code and look at the code. And we will say that we looked at the code, we inspected it, and it looks like the code is correctly merging two sorted lists. So the merge function, that's the vacuous part of the proof, is we looked at the code looked correct, so the merge function is correct. But what do we need to say now? Well, S, which is the result of merging S1 and S2, is what? This list is the union of S1 and S2, right? Which is the same as the union of L1 and L2. We're talking here sets, so there is no order, right? So all the elements of S1 union S2 are the same as the elements of union L1 and L2, right? Which is A1 all the way to AN, which is correct.
I have a question.
Sure.
Why did you do an over 2 plus 1 to get to an?
Could you think of another way to do it? Because I don't know whether n over 2 is going to be, I want it to be an integer, right?
Okay.
So I floor it.
Okay.
And then I just go to the next one.
Oh, okay. You're
Yeah.
making it into an integer.
Yeah, this part is just to make sure n over 2 is an integer.
Okay.
But because this list ended at this element, I'm just saying, go to the next one. This is part of the index. This is not. This is not this. This is A.
Oh, okay. Okay, that makes sense.
Right? Okay?
Okay, I copied it wrong.
So this is just the index. Any questions? So the proof is done. Because it's a recursive algorithm, we're going to do induction. Induction, we do base cases first. The base cases are both trivially correct. Next step is inductive hypothesis. So we assume that it correctly sorts arrays of length from 0 till L minus 1, and we would like to use that to prove that it's going to correctly sort arrays of length n. Well, because it basically splits it into two lists, each one of them has length smaller than n, then this is going to correctly sort L1, and this is going to correctly sort L2. And because we inspected the code, and merge is correctly merging two sorted lists, then we get S, which is correct, because S1 and S2 is the same as the union of L1 and L2.
For L2, why did you do n minus 4 n over 2?
Here,
Yes.
I'm trying to measure how long is this list, how many elements are there, right? So all of the elements are n. I have n elements. And n over 2 floor of them are in L1. So the remaining ones are in L2, but I would like to know, is this number smaller than n or not for all values of n larger than 2?
Okay.
Right?
Okay, I see what you did.
Yeah. Let me just write something formally. So here, we just say by inductive hypothesis on L1, we can say that this one is sorted version of L1. We could say the same thing here, but we know we're using the inductive hypothesis, right? So, any questions? Is everything clear? Okay, so now we're going to do an example to try to see how the algorithm works. What are the inner workings? How is it going to run? Before we try to measure its complexity, right? Okay, so the list is going to be so 7, 15, 2, 4, 9, 6, 8, 6, 8, 10. Right? So this is our input list. How will MergeSort work? Well, we start. Do I have more than one element? I do. So what do? We just split it into two parts, right? We create L1 and L2. What is L1? 7, 15, 2, and 4. What is L2? 9, 6, 8, and 10. Right? So now we call MergeSort. I left the algorithm so we can see, right? So we split it into two parts. Now we're going to call MergeSort on L1. So what will MergeSort do on this list? It will inspect again. Do I have more than one element? Yes. So what should you do? Split it into two parts. 7, 15, and 2, 4. And then what do? Call MergeSort on this part, right? So MergeSort will be called on this part. And what will it do? Is it larger than 2? Do we have more than one element? Yes. So split it into two pieces. 7 and 15. So now we call MergeSort on this and MergeSort on this. So when you call MergeSort on 7, what will happen? We have one element, so we just return it, because that's the base case. Right? So this function split the list into two elements, called MergeSort on this, and this MergeSort returns 7. Now it calls MergeSort on this. And this one will just return 15. What will this one do next? It's going to merge them, right? And come back here. It's going to merge them, come back, and it will return 7, 15. So this function split this list into two parts, called MergeSort on this. Now MergeSort did some recursive call and gave me back 7, 15. Now I call MergeSort on this. MergeSort will come here. I have more than one element. Well, split it into two parts, 2 and 4. Then call MergeSort on this. MergeSort will check, this is my base case, so return 2. Then I come back to here. I call MergeSort on this element, and this one will return a 4. So now what do? We merge them. So we return to here 2 and 4. Right? So what should we do now? This MergeSort split the list into two parts, called MergeSort on each one of them, and we have the return sorted lists. What should we do now? We just should merge them, right? So what do we return to here? After merging these two lists, we get 2 and the 4 and the 7 and a 15, right? So now we come back to this merge function call, which split this list into two parts, called MergeSort on this, and all of this tree happened, gave me back the result. Now I can come to this MergeSort call. When I call MergeSort on this list, what do I do? Again, do I have more than one element? Yes. So what do? You split it into two parts, 9, 6, and 8, 10. Well, you call MergeSort on the first part. MergeSort will check, I have more than one element. So again, split it into two parts, and then call MergeSort on this. MergeSort, using the base case, will just return a 9. And then come to here, call MergeSort on this element, return a 6. Merge those two elements and return 6, 9, and come to this MergeSort call. This will check, I have more than one element, so split into two lists. Then call MergeSort on this element, and we just return it. We call MergeSort on 10, we go to the base case, we return a 10. Now we reached here, both MergeSort calls returned my lists. So what do I do now? I just merge them. And I return 8, 10. Right? So now we're at this level. Now here, both MergeSort functions calls returned. So I just merge this list with this list. And I get 6, 8, 9, and 10. And we reached here, right? Because this is my list, split it into two parts, and now this merge function called returned this list, and this one returned this list. So what do I do now? I just merge them. I'm just going to write it here because there's no space. So merging is going to give me 2, and then a 4, 6, 7, 8, 9, 10, and the 15. Is the example clear? Is there any questions on how it's running? That's how the MergeSort works, yes. So one interesting thing you can see is, basically, we don't do any element comparisons until we come here. We expand this branch, come here, we come here. This is a base case, this is a base case. The first element comparison happens here when we merge the 7 and the 15. Right? This is the first time we compare elements, is to create this list. Then we come up, we expand all of this, and the second time we do element comparison is here. So, any questions? Is it all clear? Okay, if it's all clear. Now what are we going to do? We introduced an algorithm, a recursive one. We proved that it runs correctly using induction, and now we have a sense of how it runs. So what's our goal? We would like to measure its efficiency or its complexity. And we don't want to measure that in seconds, because that will depend on your machine. Or number of instructions, because that will depend on your code or the language you're using. We want to have some kind of an objective estimate of how good is this algorithm, so I can compare it with other sorting algorithms when I decide which one to use, right? So we're going to do that by counting how many comparisons will MergeSort do in order to sort this list. Okay? Let's do that. So, we agreed that we're going to measure the running time of MergeSort. Right? So, And we agreed that an objective estimate would not be seconds or number of instructions. It's going to be the number of element comparisons, right? So we're going to count the number of comparisons, right? So let's look at the code. Where are the element comparisons taking place? They only happen here, right? This is the only place that we do comparisons. In here, we don't do anything. We just call the same algorithm. We call merge. And here we're just checking is anything empty. This is the only place that comparisons take place, right? So these, the number of comparisons, all take place in merge function. So we're going to make an assumption that this is going to make the math a bit easier to handle, or at least cleaner. So we assume that n equals 2 to the k, or the k is bigger than 0, and then integer. Right? So what is this going to do? When we assume this, we just guarantee that n is going to be an even number, right? So as a result, we're not going to have any floors, we're not going to have any ceilings, right? It's an even number. So n over 2 is an integer. I don't have to worry about that. If you would like to see a proof where we make this assumption, you can check Mikkel's book, which is the course book. But in Pat's data structure book, he doesn't make this assumption. But both proofs are valid and they're going to lead to the same results. Right? So let's define this function. Let fn equal this function. It's going to be the number of comparisons done by MergeSort on input of length n, right? So we're trying to get this function, okay? So now, since we know that all the comparisons will take place only in the merge function, let's have some example. Let's try to see how it's going to work. In this example, we're going to try to count how many comparisons take place in the merge function. Okay? So let's assume we have merge here, and it takes S1 and S2. And S1 is 2, 4, 6, 8, and 10. S2 is going to be 1, 3, 5, 7, and 9. Right? So let's try to solve it, but while focusing on how many comparisons we make. Right? So S, what do we do? Compare this one with this one, right? So here I'm going to keep a counter. So that's the first comparison, right? I just made one. I copied 1 to here. I deleted it from the list. Now I compare 2 and 3, which means I have 2 comparisons. 2 and 3, 2 is smaller, so copy 2, delete it from here, and now this is the first element. Now we compare this, 3 and 4. 3 is smaller, I delete it from here, so I have now 3 comparisons. The first element is 4, first element is 5. Compare them, copy the 4 and delete it, which means I have 4 comparisons so far. Right? 5 and the 6. 5 is smaller, delete it, copy it to here. Now I have 5 comparisons. Right? 6 and the 7. 6 is smaller, copy it, delete it, compare the 7 and 8, now the count is at 6. Compare the 7 and 8, 7 is smaller, you delete it from the list, right? So now we have 8 and the 9, the 8 is smaller, copy it here. So now we have 8 comparisons so far. So now we have 9 to 10. We copy the 9 because it's smaller and we delete it from here. And now we have a total of 9 comparisons. Are we going to do any more comparisons? Well, not really. This is empty. So I'll just copy whatever is left of here, copy it to here. So how many comparisons did we make? We had a total of 9 comparisons for this example, right? So we don't want to write this in terms of a number. What is this in terms of the length of S1 and the length of S2? Well, what is the length of S1? It's 5, right? And this is 5. And in here, we made the maximum number of comparisons, right? Because we were only left with one element and we copied it to here, right? So the maximum number of comparisons we can do is basically going to be the length of S1 plus the length of S2, minus 1. A merge function taking lists S1 and S2 will at most make this many comparisons, right? But it won't have to necessarily. Let's say we have an example where S1 is 1, 2, 3, 4, 5, and S2 is 6, 7, 8, 9, then 10, right? How many comparisons will I do here? Well, let's count. You compare here 1 time, take the 1. Compare again, 2 and a 6. So I have 2 comparisons, and we copy the 2. Now this is gone, this is gone. What do? We compare the 3 with the 6. Copy the 3, and now we have 3 comparisons. 4 and the 6, we copy the 4. Now we have 4 comparisons. We compare the 5 and the 6. Copy the 5. Now we have 5 comparisons, but now S1 is empty, right? So what are we going to do? We're just going to copy this whole thing to S. So we did 5 comparisons, which means it's possible to make less on a given example, but we are trying to get the absolute worst case. We're not interested in what might MergeSort do. We want a guarantee that it will at most do this. And to make it a bit cleaner, this is obviously smaller than S1 plus S2, right? S1 plus S2 minus 1 is smaller than this. So we're just going to get rid of this one, just to make the solution a bit clean. So I'm just going to write it here, that the number of comparisons in merge function that takes S1 and S2 is going to be S1 plus S2 minus 1 at most, right? Which is obviously smaller than S1 plus S2. So we're just going to stick with this, right? So what is the length of S1 plus the length of S2? N, right? So this, in our example, it's 10, but generally, this is going to be n, right? So this f function that we defined is going to make at most the following comparisons. If we have the base case, if n equals 0 or n equals 1, we make 0 comparisons, right? But if it's not, if n is bigger or equal than 2, then we're going to call MergeSort on the first part, which is fn over 2 floor plus fn over 2 ceiling plus n. What does this mean? The number of comparisons that our MergeSort function will do is going to be the number of comparisons we're going to make on the first part of the list inside this function. And the number of comparisons we're going to do inside the merge sort that we're going to call on the second part of the list, plus the number of comparisons we're going to do inside merge. Right? Is this clear? But we made this assumption, right? So let's make use of it. Which means n over 2 floor is just n over 2. And n over 2 ceiling is just, again, n over 2. Is this clear?
So you're adding the first half of the list with the second half of the list?
No, I'm not adding. But the number of comparisons that I will do in total is the number of comparisons that I will do while sorting the first half of the list, plus the number of comparisons that I will do while sorting the second half, plus the number of comparisons required to merge them.
Oh, okay.
Right?
Okay. Yeah.
Does that mean the total is 2n?
It's actually
We're going to figure it out.
merging.
You had a question there? Okay.
Can I have a question?
Sure.
So the number of comparison you do to merge them is n, like why is that?
Because of what we just showed here, right? We had an example, and we showed that the absolute worst case is going to be actually n minus 1, right? Because the lists are sorted. Yeah, so because the lists are sorted, the maximum number of comparisons required to merge them is n minus 1, because it's s1 plus s2 minus 1, but this is n. And I want to get rid of the minus 1 to make the solution just cleaner. Okay? So this is coming from here. Okay? Any more questions? So, what are we going to try to do now? What we're going to try to do, we're going to try to get rid of this, right? We have a recurrence relationship. We're going to try to make a guess of what would this be equivalent to, and we're going to prove it with induction, right? So we just have to get rid of this and this. So So let's just copy the function from there to make it clear. So if n, the number of comparisons, is going to be smaller or equal to 0 if n equals 0 or 1. Or it's going to be 2 f n over 2 plus n if n is bigger or equal to 2. Right? I just copied it from there. So now, what do we need to do? We need to get rid of this. To do that, let's have a look, let's have an example. Right? So if I have a list of input of size n, and I pass it to MergeSort is going to split it, and here n is 2 to the k, into two lists, right? n over 2 and n over 2. And then, when I call MergeSort on this part, you can again split it into two parts, n over 4 and n over 4. And when I call it on this part, it's going to again split into n over 4, n over 4. Right? So here, n is going to be smaller than 2. What is this? This will make two calls of MergeSort on size n over 4 and n over 4, right? So this is going to be 2f n over 4. Plus it's going to merge them. What is the length total? It's n over 2 plus n over 2. Is this clear? So we're just going from here, right? The number of comparisons that MergeSort will do on an input of length n is going to be 2 times the number of comparisons on n over 2, on an input of size n over 2, right? So we're going to call it twice, plus the number of comparisons required to merge them. And because each part is n over 2, the number of comparisons required to merge them is n. But when we come to this part, right, this is going to be a merge sort call, which is going to split the list into two pieces, where each one is of size n over 4. Plus, to merge them, you're going to do at most n over 2 comparisons, because this is an n over 4 list, n over 4 list, and we have this rule we just came up with, right? So think of this as this is S1, and this is S2, and the size of this is n over 4, size of this is n over 4. So the merge function will make n over 4 plus n over 4 comparisons minus 1. We decided to ignore this, so it's going to be n over 2, right? So this is the at most number of comparisons that merge function will do when merging two lists S1 and S2 of length n over 4 and n over 4. Is this clear? So, what will this look like? It's going to be 4 fn over 4 plus, this is 2, cancels this 2, plus n. So, this is going to be 4 fn over 4 plus 2n. But if we come back to our example here, what will happen at this step? Well, this one is also going to split into two pieces, right? Of n over 8. N over 8, this is going to do the same. And this is going to do the same. Right? So let's do that again. Trying to see the pattern. We have 4 here. Just going to apply the same rule, right? So we have 2 fn over 8 plus what? Here, the length of each piece is n over 8, so their sum is n over 4 plus 2n. Right? So if we open this up, it's going to be 8 fn over 8 plus n over 4 by 4 is going to be n. And I already have 2n, so this is going to be 3n. Right? So let's take a look at this. If you look at this 3, this is level 0, this is level 1, this is level 2, this is level 3, right? So we clearly see that each step will split the list into two parts, right? Of equal size. But the question is, how far along will this tree go, right? Why do I only care about how far will this tree go? Because every level of this tree will actually make the same number of comparisons, which is n. Because here, we're going to do just n comparisons. Here, we're just going to do n over 2 plus n over 2. Here, we're going to sum all of these up. We have 4 n over 4s. And here we have 8 n over 8. And if you look at here, the pattern is clear. Every time we open it one more step, which is we expand the tree, we go from 1n to 2n to 3n, right? Is this clear? So the question is now, how far will this tree go? Well, let's think of the base case. When do we stop? The last level of this tree should be somewhere where? Okay, let's look at these numbers. What do they look like? n over 2, n over 4. So we have something that looks like this, right? N over 2 to the I. Because we keep expanding, right? 4 is 2 to the 2, and this is 2 to the 3. So we will stop when we reach this condition. This is going to be the last level we expand. We don't know what I is, but we're going to stop right before we reach size 1, right? So what does this mean? Let's put this. That's going to be more accurate. So what does this mean? It means that n is going to be bigger or equal than 2 to the I. Okay? What can we do here? We can basically take the log, right? So, what is going to be the log of 2 to the I, log base 2? log base 2 of 2 to the I. It's going to be log 2 to the n. It's going to be I log 2 base 2. This is 1. What does this mean? It means we will expand, because here I is the number of levels. We're going to expand the tree, right? We're trying to find that out. And it's clear that I is going to stop at log 2 to the base n. Is this step clear? We're just trying to make a guess. We're looking at this tree, and we're realizing every time we expand the tree, n gets divided by 2, right? We're trying to guess when will this tree stop. So this is going to continue n to the 16 and so on until we reach a number, which is n2 to the I. This is going to meet the base case of MergeSort, right? And because we know the base case is 1, this means that we're going to expand the tree this many times. Is that clear? Ask me if you have a question. Because we're going to expand this tree this many times, and because we know every time we do that, we just add one more n. So we can make sort of a guess that, let's clean this part, we can make a guess that we're going to have n log n at most many comparisons, right? We're just going to make a claim. We're going to make a claim that for n equals 2 to the k, where k is bigger than or equal to 0, and then integer, right? That MergeSort does at most n log base 2 of n comparisons. Because we defined a function that counts how many comparisons, then we're just saying that fn is smaller or equal to than n log base 2 of n. Right? This is how we solve any recurrence relationship we get. We try to just look at the problem, try to expand it a bit to see a pattern. And that's what we did here. We saw the pattern that each level, each time we expand the tree, we gain an n. So we just needed to count how many times are we going to expand the tree. And because each level, we stop whenever we reach 1, and each one is dividing n by 2, we're going to stop once we're going to expand the tree log base 2 n times. That's it. So we're just going to make this guess. But we need to prove it, right? So we do that using induction again. Right? We made a claim, now we prove it, we use induction. So what is the base case? Now, because we assume that n takes this form, our base cases are no longer 0 and 1. Why? Because n cannot be 0, right? If k is an integer bigger or equal to 0, then the smallest value n can take is 1. So here we just have to care about one base case, which is n equals 1. So what happens when n equals 1? How many comparisons do we make? Well, we know that MergeSort from here, right? We did it here. MergeSort does 0 comparison. 0 comparisons. Does 0 comparisons. Right? We know this to be true. Now let's check. will that give me the same thing? So if n, when n is 0, is smaller or equal to 0 multiplied by log base 2 of n. No, n is 1, I'm sorry. 1 log base 2 of 1. Right? So log base 2 of 1 is 0. So this whole thing is 0. So f of 1 is smaller or equal to 0, which is correct, because this is equal to this. Right? So now what do we need to do? It's an proof by induction. We did the base case. What should we do now? Inductive hypothesis, right? So let's assume that this is true, which means this claim is true for arrays of length 1 all the way till n minus 1. And we want to prove it for n bigger or equal to 2, right? So what we're trying to prove is this. This is our goal. So we usually do this by going to the recurrence relationship, which is here. If n is bigger or equal to, no, smaller or equal to 2, fn over 2 plus n. And we try to use our inductive hypothesis to reach here. So let's try to do that. No need to write this all the time. So this part is equal to 2 multiplied by what? What is fn over 2? Because n over 2 is obviously smaller than n. Actually. Right? No, is it? No, it has to be smaller than n. Because we covered the base case 1. So n over 2 is obviously smaller than n. Which means it's covered by our inductive hypothesis, which means that this is true. So what we write is fn over 2 is going to be n over 2 log base 2 n over 2 plus n. Okay? Which is equal to, this 2 will cancel with this 2. You can have n log base 2 of n over 2 plus n. But that's not what we're looking for, right? Anybody has an idea of what to do with this? Some properties of logarithms? Do you guys remember this? What is this? Absolutely. So this is this, right? So let's try to use it here. So log base 2 of n over 2 is going to be log base 2 of n minus log base 2 of 2, which is equal to log base 2 of n minus, what is this? That's 1, right? So this, we can bring it here, right? Which means this is going to be equal to n multiplied by log base 2 of n minus 1 plus n, which is equal to n log base 2 of n minus n plus n. The n's will cancel. We get n log base 2 of n, and that's what we're looking for, right? Yep. We just reached the part that we're looking for, right? Which means our guess for the complexity of this algorithm is correct, because we just proved it by induction. We did the base case, we did the inductive hypothesis, and using the inductive hypothesis, we reached what we're looking for, right? So now we can safely say this. The running time of MergeSort on a list of length n is right. Do you know what this means? This is called big O notation. So this actually means a family of functions, but you can think of it as this is going to be multiplied by a constant, and this will form an upper bound on whatever we're trying to measure. So what we just proved that is the running time of MergeSort is at most some constant multiplied by n log n. So what does that mean? Let's say that n is 2 to the 20, right? That means that n is 1 million, right? So how many comparisons will MergeSort do in order to sort a list of 1 million elements? It's going to make 20 million. And that's a pretty good number, considering that it's required to sort 1 million elements. How about this? Here we have 1 billion elements. Right? So if each element is a byte, that's going to be roughly a gigabyte. If you have an array of 1 gigabyte, and if you want to sort it out, how many comparisons will it make? It's going to make 30 billion. Question? I'm not that good, so you should have questions. Or you're all extremely confused. Sure. Let me just check the time. Sure.
When you were doing fn less than log 2n minus 1 plus n, you made two different versions of that.
What do you mean?
Like over there you did the calculations for here, and over there you did the same thing for that, different things for that equation.
You mean here and here?
Yeah.
No, I started with here, and I reached here, and I just copied this till here. And then I used this rule here to replace this with this. Any more questions? Thoughts? Is it what? Yeah, but we're trying to measure how good it is in terms of time, which means how many comparisons will it do? Okay. I think we're going to discuss this by the end when we study when we take the expectation of random distribution, because we now have MergeSort. We're going to have another one that has randomness in it, and then we're going to compare it. Okay?
Is it stable though?
What do you mean stable?
Does it replace the same number but index? Imagine I have 4, 4. Does it switch the index of those 4, 4?
I don't understand.
Imagine there's two items in the array has the same number. Does it switch the positions?
Yeah, it has.
It has to, like even they have the same number, like one of the 4 is on the 3rd index. The other
You mean if there is a 1 here and the 1 here and they're the same number, right?
Yeah.
It will depend on how you handle if they're equal. So that will depend on your code. You You can say take the first one, or you can say take the second one. Okay. Sure.
We did log 2n minus log 2.
2, because log 2 to the base 2 is 1.
Oh, okay, that
Right?
makes sense. That makes sense.
I'm already hard.
But I would. Sure. You were multiplying that by n. Why didn't you multiply n into that?
No.